Now, this brings us to a good point where we can look at a few transform pairs. You can almost look at these by inspection, but let's just, I'll work it out on the right hand side. Okay, for property number 1, that means the sequence has got only a value of 1 at n equal to 0. So x of z equal to 1, because when you do the summation, only one term is there. The ROC, there are no positive powers of z, there are no negative powers of z, so the entire z plane, this is the ROC. It's a constant. So therefore, we can put a tick mark to this particular one. Second one, u of n, we have just now computed. Let us just quickly write that down. X of z equal to summation n equal to 0 through infinity z inverse. So this will be 1 over 1 minus z inverse mod z greater than 1. I'm sorry?
Z raised to minus n.
Right. This should be minus n. Correct, yeah. So this will give us mod z greater than 1. Okay, so this one. And if you just go back and look at the previous chart, we also looked at u of minus n minus 1, and we showed that they both have the same u of n and minus u of minus n minus 1 have the same z transform, only that the ROCs are different. So therefore, we can put a tick mark on this as well. Now delta of n minus m, let us take m equal to 2. So in this case, the sequence is 0, 0, 0, 0, 0, 1, 0, 0, 0. Okay, and the origin is here. Okay, at a delay of 2 units, you have sorry, it should be green. At a delay of 2 units, you have a single non-zero value. So therefore, x of z will be z power minus 2. Okay, because negative powers of z, we have to exclude z equal to 0. Exclude z equal to 0. But we can include the entire z plane, the rest of the z plane. Okay, now, if m had been minus 2, then what will happen? Z equal to infinity would have been excluded. So whenever m is greater than 0, you will find that 0 is excluded. Whenever m is less than 0, you will find that m equal to z equal to infinity is excluded. So basically, you have a entire z plane. One of the two extremes will get removed because of that particular condition. So we can tick off that. Okay, a of n, u of n. Actually, u of n is a special case. When a is equal to 1, you get that. So you can look at whatever you have done for u of n exactly similar. You will find that the expression for x of z is 1 over 1 minus a z inverse, and it's mod z greater than modulus of a. So basically, this is also a simple geometric series, and we also showed that when you look at it as a left-sided sequence, you will get the same z transform, but mod z will be less than the pole. So this is also related to that. All right. Now comes the property of differentiation, which we have. I believe we have already written it down. But if not, I mean, if you don't remember what we had written, we will write it down very quickly. So basically, the property of differentiation will go as follows. Okay, so let me just see what is the best way to express this property. Okay, so let's look at number 7. Maybe I'll add a extra page, and we will write down x of 7. Okay, so property, our transform pair number 7, x of z is equal to summation n equal to minus infinity to infinity x of n z power minus n. Okay, so if I differentiate d by dz of x of z, treating z as the variable, I am differentiating first derivative. This will be d by dz of n equal to minus infinity to infinity x of n z power minus n. X of n is a constant, does not depend on z. So what we have here is taking the derivative inside, n equal to minus infinity to infinity x of n minus n, power base angle rule, z power minus n plus 1. Okay, just rewrite it a little bit. You get minus z summation n equal to minus infinity to infinity x of n times n. So this is the term that we are interested in, z power minus n. Okay, so this is d by dz x of z, minus sign, yeah.
Minus 1 by z. Equal to minus 1.
Oh, z power minus 1, yeah. Z power minus 1, correct. So this is equal to d by dz x of z. Okay, just taking the z inverse to the other side, what we get is minus z d by dz x of z is equal to summation n equal to minus infinity to infinity n times x of n z power minus n. Okay, so this basically gives us a z transform relationship which says n times x of n can be related to the z transform of x of z, of x of n in the following manner. It is minus z d by dz x of z. Okay, this is a useful result to always keep in mind. Now, what is the expression that we have here? We have a sequence which is n times a of n u of n. Okay, so the first thing that you will do is a of n, use a different color, a of n u of n has got a expression which is 1 over 1 minus a z inverse mod z greater than a. Okay, so from the expression that we have, n times a of n u of n must have a z transform minus z d by dz of 1 over 1 minus a z inverse. Okay, just go ahead and apply the differentiation and you will be able to verify that what you get here will be a times z inverse 1 minus a z inverse the whole squared. Okay, now important question, what about the region of convergence? Okay, now the important question to answer is it still a right-sided sequence? Yes, n times a of n, u of n, it's a right-sided sequence. Okay, now did the pole change? Location of the pole. What was the original of u of n? What is the z transform of the x input? It is 1 over 1 minus a z inverse. The pole was at a. Now you have an expression which is 1 minus a z inverse whole squared. That means there are two poles, but both the poles are at z equal to 1, z equal to a. So therefore, the location of the poles also did not change. So therefore, the ROC still remains the same. ROC is still the same poles, it has to be outside of the furthermost pole, and the single pole became a double pole in the Z transform, but does not matter, the location of the pole is all that matters, and therefore mod Z greater than A. So go back to this expression. So what you find is that it is a expression that we can derive where is mod Z greater than A. So please verify. Okay, this we have done. Now this is something that I would like you to verify. Basically, for a left-sided sequence, write down the Z transform and then go and do the differentiation. And again, it's only a matter of applying the things in a correct manner. All right, we will come back to the remaining ones. Those are simple, but I would like to take you to look at one more example before we look at this these examples. Okay, so let us look at the following. Let me just remember which one. So our table is on page 16. Okay, we'll have to come back to this after some time. Now I'm going to look at a very detailed and important discussion on the region of convergence. Okay, this is an important example. I would like you to pay very close attention and use this as a way by which we can understand a lot of the aspects of the region of convergence. Okay. We are given a transfer function which is in rational form, a constant k, 1 plus 4 z inverse, 1 plus 2.5 z inverse divided by 1 plus 3 z inverse, 1 minus 1.5 z inverse, 1 minus 0.9 z inverse. Okay, I hope you are looking at this particular aspect and are able to write down the or look at the expression. First one is I want to look at the poles and zeros. Okay, always good idea to start off by looking at the poles and zeros. Okay, where are the zeros? Zeros are the zeros of the numerator polynomial. Z equal to minus 4, Z equal to minus 2.5. Those are the two zeros that we have. The poles that we have, very important because this is what will impact on the region of convergence. Z equal to minus 3 corresponding to the first factor. The second one, Z equal to 1.5, and the third pole Z equal to 0.9. Okay, hope you are able to see that and are able to look at that as a way by which we can understand this particular example. All right. So now what we would like to do is to write down a simple way of dealing with this particular example. So the first step I would like to do is the partial fraction expansion. Partial fraction expansion. We had already explained what partial fraction expansion is. So this is writing it in the following form. We have three poles, three are all distinct poles, so we can write it as a constant a1 divided by 1 plus 3 z inverse plus a2 divided by 1 minus 1.5 z inverse plus a3 divided by 1 minus 0.9 z inverse. Okay, so basically partial fraction expansion, you can see how you can take the common denominator and then cross multiply, and then you will get equations for a1, a2, a3, and then you can solve. So basically we will assume that we have computed. So assume a1, a2, a3 are computed. a1, a2, a3 are computed. Okay, they will be some constant value, so it won't affect our decision. Okay, so the first thing that we would like to do is to look at the regions of convergence and look at how we can. But maybe the easier thing would be is let us first sketch the poles. maybe that will be easier for us to do. Okay, the first pole is at z equal to -3. There's a pole at z equal to -3. And then there is a pole at 1.5, half that distance. And another pole which is at 0.9. Okay, so this is 0.9, this is 1.5, this is -3. Okay, so always helpful if we can draw 3 circles. So the first circle is the one that touches the first pole, the second circle second circle, and then the third circle, which is the radius equal to 0.3, radius equal to 3. Okay. So you'll have to imagine them as 3 circles, concentric circles. Okay. So now the possible regions of convergence that we have. Okay. So first one, ROC1. ROC1, I want to get a right-sided sequence. So therefore, I take mod z greater than the outermost pole, mod z greater than 3. Okay. Please write down the sequence for me. It will be A1 minus 3 raised to the power n u of n plus A2 1.5 raised to the power n u of n plus A3 0.9 n u of n. Okay, I hope you are comfortable with that, and we can look at this as a way of understanding the sequence that we have obtained. Okay, so in this case, all 3 are right-sided sequences. So I will just put down saying 3 right-sided sequences. 3 right-sided sequences. Now, there's a second region of convergence, ROC2. Remember, first one is outside the outermost circle. Second one is between the 2 poles, 1.5 and 3. So the region of convergence is mod z. It cannot include any of the poles. So it will be greater than 1.5, less than 3. Okay, so the sequence corresponding to z equal to 3 will now be a left-sided sequence because you're taking mod z less than 3. So here is the expression for the sequence. Okay, it will be minus A1 minus 3 power n u of minus n minus 1. Okay, that will be the sequence that corresponds to A by 1 plus 3 z inverse when you want it as a left-sided sequence. Plus A2 right-sided sequence 1.5 raised to the power n u of n plus A3 0.9 n u of n. Okay, so in this particular case, you have 2 right-sided, 1 left-sided sequence. I'm just going to use short form R and L for the two sequences. Okay, quickly let's write down 2 more regions of convergence. ROC3 will be mod z greater than 0.9, less than 1.5. Okay, in this case, you will get 1R and 2L. Okay, and then the last one will be ROC4, where you will get all of them to be left-sided sequences. 3 left-sided sequences. 3 left-sided sequences. Okay. Now the important thing to note to answer is which of these sequences is bibostable. Remember, this is another way of asking for which of these sequences the DTFT exists. Okay, bibostable means the impulse response must be absolutely summable. This is a transfer function. So if the impulse response is absolutely summable, its DTFT will exist. So basically, for which of these sequences will the DTFT exist? Now, important thing to note is where is the unit circle? Unit circle lies very close to this innermost circle, that is pole at 0.9. So this dark blue circle, dashed circle is the unit circle. Okay, so this is mod z equal to 1. Which of these region of convergence? The first one is region of convergence 1. This is ROC2, then you have ROC3, and then you have ROC4, innermost all side. Okay, so this is true only for ROC3, because that's the one that has got the unit circle. Because the unit circle is there, the DTFT will exist, and therefore it will be bibostable. So you can write down the sequence for which it exists. That will be for mod z greater than 0.9, less than 1.5. That is the ROC that we are interested in. And again, if you want to, if you are asked to declare, is this sequence, is it causal, anti-causal, what type of sequence is this? It is a non-causal sequence, because you will have, it produces one right-sided sequence and two left-sided sequences. So therefore, this is a non-causal sequence, but it is absolutely summable, and therefore the discrete time Fourier transform will exist. For the other three, because the unit circle is not included in the ROC, we can state confidently that those are cases where you will not have the region of convergence included. Okay. I hope you have had a time to think about it. Please do think about it, apply several concepts. First one is to say that ROC depends only on the poles. The zeros don't matter. So we take the poles, do a partial fraction expansion. From the location of the poles, we can get these concentric circles, and then you decide, do you want to do how many ROCs are there? In this case, there are three concentric circles, so therefore there are 4 regions. 4 ROCs can be thought about, and each of these ROCs will have a unique characteristic in terms of number of right-sided sequences, number of left-sided sequences, and also which of these sequences is bibostable. Only one of them will have the region of convergence, will include the unit circle, and that is where you will find the expression that is of interest to us. All right. So with that, we can also look at another example which will be helpful for us to apply the results that we are looking at. So the second example. Okay. So we go back to 16, and actually, we're not okay. We have to come back to 16. All right. So here is another example. This is there. This is there in the table. But let's do that, and then we'll go back and look at what's there in the table. R naught raised to the power n sine omega naught n u of n. Asked to compute the Z transform. Okay. So we write this as 1 by 2j R naught raised to the power n e power j omega naught n minus R naught power n e power minus j omega naught n. This is an u of n. Okay, this is the expression that we have. So the corresponding Z transform will be summation n equal to 0 to infinity. That's because of u of n. There's a 1 over 2j outside. R naught power n e power j omega naught n z power minus n. Then there is a minus 1 by 2j summation n equal to 0 through infinity R naught power n e power minus j omega naught n z power minus n. Okay, these are both geometric series. So we can write down the closed form expression. So let me pull 1 by 2j outside by 2j. This will be 1 over 1 minus r naught e power j omega naught z inverse under the condition that mod r naught e power j omega naught z inverse is less than 1. This is the same condition that mod z is greater than r naught. Okay, the second term. The second term comes out to be with the minus sign 1 divided by 1 minus r naught e power minus j omega naught z inverse. Apply the conditions. This will be modulus r naught e power minus j omega naught z inverse. This has to be less than 1 for the geometric series to converge. This produces the same condition that mod z greater than r naught. Okay. So under the condition that, so the ROC is mod z greater than r naught. Okay. And if you remember, we also did a factorization of this type. So if you can do the following, 1 by 2j, take the common product, 1 minus r naught e power j omega naught z inverse multiplied by 1 minus r naught e power minus j omega naught z inverse, and then numerator it will be 1 minus r naught e power minus j omega naught z inverse with a minus sign 1 minus r naught e power plus j omega naught z inverse. Okay, so the minus ones will cancel, and what you will be left with is a very compact form, which is what is given for us in 16. So basically what we have just now solved is this example. Okay, so what we have, this will be equal to, if you combine these two terms, the numerator will be 1 by 2j r naught e power j omega naught minus r naught e power minus j omega naught z inverse. Okay, that's the numerator, divided by 1 minus 2 r naught cosine omega naught z inverse plus r naught squared z power minus 2, and this term is nothing but r naught cosine, r naught sine omega naught, r naught sine omega naught. Okay, r naught sine omega naught z inverse numerator, denominator is given here. Go back and look at number 16, r naught sine omega naught z inverse, and the condition is mod z greater than r. So I'm going to put a tick mark that we have just been able to verify that. Exactly the same method, you expand cosine omega naught n, you will get number 11. You set r equal to 1, you will get 9 and 10. I'm going to tick off all of these with one stroke. Okay, so the last of the expressions that we are going to work with is that finite length sequence. Remember, we wrote down that you have, let's say, number 13. Okay, ax of n is equal to a power n in the region n equal to 0 through n minus 1. Okay, and if you remember, we wrote down this is a finite length sequence, and we said that this can be written as 1 minus a n z n divided by 1 minus a z inverse. There is a pole at z equal to a, but that will cancel, there will be a pole 0 cancellation. So the pole 0 cancellation will be there, and because of the pole 0 cancellation, there are no poles except at z equal to 0. So the ROC will be entire z plane except z equal to 0. Entire z plane except z equal to 0. So which is the same as saying mod z strictly greater than 0. Equal to 0 is not allowed. Anything greater than 0 will be allowed as a valid. So this is the expression that we have for this sequence. All right. Now this is a useful point at which we say that, okay, we have got a good understanding of how to compute the Z transform. We know how to look at the regions of convergence. We know how to specify the region of convergence. We know how to factorize them, do partial fraction expansion, and get the combined region of convergence.